Okay, section 12.2 is all about inverse functions. So we have a good amount of stuff to do in this section, 5 things in our objectives list here. Some of them go pretty fast. So the first thing before we get into inverses, we need to define what's called one-to-one functions. One-to-one functions. So this is a property that some functions have and some don't, and we want to define it and figure out how to test for it. And that test that we use is the horizontal line test. Line test, or HLT, because I'm lazy. The third thing is now once we have one-to-one, we can talk about function inverses. We can talk about graphing inverses. And then finally, we can determine if two functions are inverses. So let's define what it means to be one-to-one. One-to-one functions. So a function f of x is called one-to-one if every y value has only one x value associated with it. Now, the definition of one-to-one is very similar to our standard definition of a function. Remember, a function is a relation that says the relation is a function if every x value has only one y value associated. So this is kind of the opposite. So you can think of one-to-one as if you are an x value, you only go to one y value, and if you're a y value, you only came from one x value. Because we know we can have functions that have multiple x values with the same y value, and one-to-one functions do not have that. So let's look at a little example here. So we are going to let f be the function defined by the set of ordered pairs 6, 2, 5, 4, -1, 0, and 7, 3. And g be the function defined by the set 3, 9, -4, 2, -3, 9, and 0, 0. And we want to know which of these is one-to-one. Which is one-to-one. So the thing that we look at when we're dealing with one-to-one is y values. So if every y value has only one x value, that means that there should be no repeated y values. So in our function set f, every single y value is unique. So we would say that f is one-to-one. No repeated y values. But now if we look at g, we have 9, 2, 9 again. And I don't even need to look at what the last one is. Just from these 2 points, I have a repeated y value, which means that we are not one-to-one. So G is not one-to-one because the value 9 is repeated. And that's as simple as it is. You just look for repeated y values. Now obviously when we have the ordered pairs explicitly like this, that's easier said than done. And so that's why we need a better mechanism than just brute forcing and looking at all of our points. Because if we have a function that's defined by an equation, we know that that has infinite points, and that's harder to do. So that's why we have the horizontal line test. So if you have points, you can just look at your y values. But if you don't, the horizontal line test is the best way to test for one-to-one. Horizontal line test, or the HLT. And luckily, this works just like the vertical line test, but with a horizontal line test. So this tests whether a function is one-to-one, and it looks at, or says that horizontal lines should only cross once for a function to be one-to-one. So vertical line tests graphs to see if they're functions. Horizontal line tests, once you already know it's a function, you're testing whether or not it's a one-to-one function. So let's look at a couple examples. Since this works just like the vertical line test, this shouldn't be too new, too different. We've been doing the vertical line test a little bit already. So let f of x equal mx plus b, and we'll let g of x equal ax squared. So two general functions. So for mx plus b, let's say that this point right here is 0, comma b, and then our line would go through that point like this. Now it's a line, it's linear, we already know it's a function, and so we just look at horizontal lines all the way through. None of these are going to cross the line more than once. They'll all only ever cross that line in one exact point, which is what we want to be one-to-one. So this passes the horizontal line test, which means we call it a one-to-one function. And since we've done this for the general linear function, we can say with certainty that all lines are one-to-one. Now, for g of x, ax squared, if we look at ax squared, we know that that's going to go through 0, 0, and then it'll do something like this. Now, no matter what horizontal line we pick, we're going to cross in two places, and that's bad. So this fails our horizontal line test. Fails the horizontal line test. So that means this is not one-to-one. So horizontal line test, very, very similar to the vertical line test, only horizontal lines. and it tests something a little bit different. So now what we want to talk about is, why do we even care? What does it mean to be one-to-one? Well, we have a very important theorem in algebra, and this theorem says if f of x is one-to-one, then it is invertible. And to be invertible, this means that we can find the inverse function of f of x, and we denote that f with a -1. So this is not f to the -1. We read this literally as f inverse of x. So anytime you see a -1 before the parentheses, that means inverse. So if it was after the parentheses like this is equal to 1 over f of x, like we're used to using reciprocal laws. But if it's before the parentheses, it is not equal to this. So this is not f inverse. These are very, very different notations, so keep a lookout for that and make sure you're not thinking of it as a reciprocal. So this is the big reason why one-to-one functions are so important, because only one-to-one functions by this theorem are the functions that have inverses. Now that's not to say that the relations can't be inverted. It just means that when we say inverse, it means we can find specifically an inverse function. And so not only can we invert f of x, but we can find this f inverse of x, and this is a function itself. So let's take a look at how we find inverses. Finding inverses. So if f is a set of ordered pairs x comma y, then its inverse, f inverse, is the set of ordered pairs y comma x. So essentially, finding an inverse boils down to flipping the x's and the y's. Now, as we'll see for the rest of this section, this is true no matter what type of function representation we have. So let's start with ordered pairs like we did in the initial example for one-to-one functions. So let's say f is the set of ordered pairs 0, 1, -2, 7, 3, -6, and 4, 4. And we want to know what is f inverse is. Drop my pen. Well, f inverse, as our little statement up here says, we just switch all of the x's and y's and flip them. So instead of 0, 1, we have 1, 0. Instead of -2, 7, we have 7, -2. Instead of 3, -6, we have -6, 3. And instead of 4, 4, we have 4, 4. Now, if you're ever unsure of whether you should have inverted the function or not, and you forget, remember it's all about your y values. So now, for this to be a function, our x values need to be unique. Well, if the x values are unique in f inverse, then that means that the y values in f needed to be unique. This is why being one-to-one and being invertible are the same thing. So you're always looking at for f inverse your y values in f to be unique, and when you construct your inverse you should have a function again. So this is all well and good if we have ordered pairs, but we know that we don't work with ordered pairs function representations very much. We work mostly with equations. So how do we find the inverse? The inverse of an equation. Well, number one, we replace f of x with y. So all of our functions always come in function notation. When we're converting into inverses, we want to just switch it back to the y notation. After we've done that, we switch x and y locations. So in your equation, everywhere where there was an x becomes a y, everywhere where there was a y becomes an x. So this is the flipping that we did in the ordered pairs. We're always swapping locations of x's and y's to find an inverse. After that, we solve for y. And then once we've solved our new equation for y, we replace y with f inverse of x. Back to function notation and distinguishing our new function from the old one as its inverse. So let's try this out on a couple functions. So we're going to find the inverse of f of x equals 9 over x minus 1. So step 1, replace f of x with y. So we have y equals 9 over x minus 1. Then I'm going to flip positions. It becomes x equals 9 over y minus 1. And now I need to solve for y. So I'm going to multiply both sides by y minus 1 times x equals 9. I'm going to divide both sides by x. We get y minus 1 equals 9 over x. Add 1 to both sides. We have y equals 9 over x plus 1. Then step 4, replace y with f inverse of x equals 9 over x plus 1. I found the inverse. So let's call this A. Now for B, I'd like you to try the same thing for 3x plus 5. So start by just following our 4 steps. And pause the video and work this out. Okay, so I'm going to go through this now. I'm going to make this y equals 3x plus 5. Switch my x and y spots. X equals 3y plus 5. Minus 5 minus 5. X minus 5 equals 3y. Divide by 3, divide by 3. Y equals x minus 5 over 3. And then switch back to function notation. F inverse of x equals x minus 5 over 3. That's our inverse. So the homework's going to have plenty of problems for you to practice finding inverses, but this is the process no matter how complicated the function is. You just switch your x's and y's and solve for y again. So let's talk about how do we graph inverses. So of course we could solve for f inverse and then graph it, but what if we're not given the function? What if we're only given f of x? So we have a little procedure for graphing inverses. to graph the inverse of f of x, the first thing we do is graph f of x. Then we graph the line y equals x. And then we reflect f of x over y equals x. This represents the flipping of the x's and the y's. So when we reflect over that line, we are changing all the x's from f into y's and all the y's from f into x's. That's what that flip is, just like the flip here, and just like the flip with the ordered pairs. So let's look at a nice little example of how this would work. Luckily, it means that we don't have to learn any new tricky procedure for graphing. If you can graph any of the functions that we've been graphing so far in class, up to this point, you can graph any inverse. So we're going to graph f inverse of x if f of x equals x cubed. So we've done, or we could figure out the inverse of x cubed, but we're not going to do that. We're just going to graph. So 1, 2, 3, 4, 5, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8. Negative 2, negative 4, negative 6, negative 8. Negative 2, negative 4, negative 6, negative 8. 2, 4, 6, and 8. So we're going to start by graphing x cubed. So x cubed goes through 0, 0, goes through 1, 1, goes through negative 1, negative 1, goes through 2, 8, and it goes through negative 2, negative 8. And it looks as best I can here like this. So that's f of x. Then we graph the line y equals x. Now y equals x goes through 0, 0, 1, 1, and negative 1, negative 1. So I don't need to graph anything new. I'm just going to make the line here. So that's our line y equals x. And now to reflect, the idea is that these points go at a 90-degree angle to this line. Now my scaling's a little off, so it won't be perfect, but you don't need to use a ruler to do this. You know your points. So this was 2, 8, which means our inverse point goes to 8, 2. About right here. 1, 1 stays on 1, 1. 0, 0 stays at 0, 0. And negative 1 stays at negative 1, negative 1. But negative 2, negative 8 flips to, instead of negative 2, negative 8, we need to flip it to negative 8, negative 2. So negative 8, negative 2 down here. And then we connect it like this and like this. So you can see that it looks pretty good, pretty perfectly reflected. This piece over to here and this piece over to here. And if I were to draw a line through this, mine's not going to be perfect. The idea is that on a scaled axis that's completely equal, you can see my distance between 1 and 2 and 1 and 2 is not quite the same. That's why we're not getting the nice 90-degree. But let's say you're graphing this on the homework in the pre-constructed axes. those are going to be perfectly down to the pixel scaled. And so your line, if you connect one point from F to the corresponding point on F inverse, you will make a perfect 90-degree cut in that line y equals x. On paper, we're human, so we're going to make mistakes a little bit in our scaling. We can't be perfect down to the pixel, but it looks pretty good. Obviously, we know that I'm not the best at graphing, so it's not a perfect 90-degree angle through that y equals x, but it's fairly good. It looks pretty straight. But that's how you graph. Start by graphing your first function, graph y equals x, and then just flip all of your points to the opposite points. So this one, -8, -2. So now we've seen how to find inverses of equations, of points, and of graphs now. The more common thing that we get told to do is, here's two functions, tell me if they're an inverse. So this is how to determine if two functions are inverses. So if f of x and g of x are inverses, then f composed with g of x, which is f of g of x, should equal x, and g composed with f of x, which is g of f of x, should also equal x. Now you do have to check both of these. F circle g and g circle f, you have to verify that they both work. There are some unique functions that f of g of x equals x, but g of f of x does not. So you don't just get it for free. You can't just check one. You got to make sure you're checking both. So let's look at an example or two, maybe three. So determine if f of x equals 5 over x is its own inverse. So what this means is that f inverse of x equals f of x. That's the question we're asking. So we are going to compose f with f. So f circle f of x is f of x, which is 5 over x, which is 5 times x over 5, which equals x. Now, since we're composing f with itself, we don't need to do both because f circle f is the same as f circle f. So we can say that f inverse of x equals f of x. So that was a bit of a unique one where we're asked to determine if a function is its own inverse. More commonly, we'll be given two functions and said check to see if these are inverses. So let's try a couple more here. So determine if the following pairs of functions are inverses. So number one, f of x equals 4x minus 1, g of x equals x plus 1 over 4. Number two, f of x equals x squared, and g of x equals square root of x. So you know how to do this, compose the two functions, f with g, g with f. So I would recommend you pause the video and try these out on your own. I'll walk through them one at a time, so if you get stuck on the first one, hit play and watch how I do it, and then try number 2 again on your own. So f circle g is f of g of x, which is 4. Replace x with everything of g, x plus 1 over 4, minus 1. 4 times 1/4 will cancel, x plus 1 minus 1, that equals x. Okay, we're only halfway there though. G circle f is g of f of x, which is replace x with all of f, 4x minus 1, plus 1 all over 4. 4x minus 1 plus 1 is just 4x, divided by 4 equals x. So f and g are inverses. So if you haven't done number 2, you should pause the video and try number 2 here. But f circle g is f of g of x, which is replace x in f with all of g of x, so that's the square root of x squared. We know the square root squared undoes itself, so this is just x. And g circle f equals g of f of x, so the square root of x squared. We know again, the square root of a square gives us x or negative x. Remember in chapter 10, maybe it was 11, they're bleeding together, but in the last chapters, when we square root now, we have 2 answers. So this is good enough for our purposes. So they are inverses. F and G are inverses. Square root of x is a bit of a special case, and x squared, because if you remember, when we did our horizontal line test example, where'd it go? We used the square root of x to show that it fails. Well, that's very interesting, because here we're saying that it is invertible. So what we're actually saying with the square root is that algebraically it has 2 inverses. So the square root of x is the inverse of f of x equals x squared, with the restriction that when x is strictly greater than or equal to 0. Because we know we can't put negatives into that. And secondly, the negative square root of x is the inverse of f of x equals x squared when x is less than 0. Now, the thing to remember here is this restriction is not placed on the inverse, it's placed on f. So if we think about f of x equals x squared as a piecewise function, it equals x squared if x is greater than or equal to 0, and it equals x squared if x is less than 0. Yes, this does collapse back into its own self, but we do this because now we can invert it. So x squared when x is greater than 0 will look like this half. Well, if this goes through the line or gets reflected across the line y equals x, we can reflect it and it would look like this would go here and it would look like this. My line's really bad. But it would do that. If we have, put it over here. Let's see if I can draw some better lines here for you. The other one, the other side, this is x squared when x is less than 0. Not including 0 though. So this is a point and this is a hole. And we reflect across this line again. Well, this reflected does this. So this here is x squared. This is the negative square root of x. This is still x squared, and this is the positive square root of x. So we can invert the quadratic x squared if we separate it into two pieces. And we invert one at a time. And if we put them together, the inverses that is, not the x squared, our top half gives us this, our bottom half gives us this. And if we were to draw the line, y equals x, and reflect these back, we would get this, and we would get this, which is our x squared. So the two branches of the square root, the positive and negative root, are algebraically the inverse of x squared. But we can only think of them in this special case where we are splitting the quadratic into its positive and negative branches. Positive x here, negative x here. So that's the end of 12.2.